Good afternoon, good morning, everybody. We are talking about applying real world problems. So, applying exponential equations, logarithmic equations, even logistic equations, they're all related. Exponential equations, we know that is when the unknown is in the exponent spot. And if we have exponential functions, we need logarithms to undo that. This first example is a logistic function, and it behaves like an exponential up to a certain point. Logistic functions taper off eventually, and they are applicable in all sorts of places. Population, we all know that population grows exponentially, but not indefinitely. I mean, the population of my fish tank, the fish are reproducing exponentially, but it's not like if I just continue to feed them, I'm going to end up with 10 million fish because I've only got a finite amount of water, a finite amount of resources. So the fish will naturally stop producing. They will stop growing exponentially because they've saturated like their environment. They've reached the full potential of their environment. So their reproduction tapers off. So let us begin. This is a real model based on 20th century census data, and this is supposed to predict the population of New York State in millions based on time in years. And we've got 4 or 5 questions here. What's the pop? This is all for t values, all for years after the year 1800. So my first question is, what was the population of New York in 1800? When will it? What will the population be in the year 2024? And this year, 2020, there are 19.45 million people living in New York. And how close was the model in predicting that? What does 19.875 mean? What is this? What is the significance of this number? And finally, when was the population of New York 10 million? So I lost track. 6 problems. I don't know. But let's begin. What was the population of New York in 1800 based on this model? This model predicts population for all the years after 1800. So, in other words, when t is 0, that is 1800. Also, the y-intercept when t is 0. So, I'm going to replace t with 0. And I've got this. Now, I don't need my calculator just yet because I know this negative 0.035005 times 0 is, of course, just 0, and e to the 0 is 1. So 1 plus 57.993 is 58.993, and I divide, and this is the first time I need my calculator, 0.337. What does that mean? Does that mean that in 1800 there was, am I wrong here? Were there 0 people in 1800? I don't think so. New York was established before the independence of our country. So was there a third of a person? We have to remember that P is the population in millions. So there was 0.337 million people in 1800, which is 337,000 people in 1800. As a rule of thumb, if you are given words, in other words, a word problem, your answer must be in words. So you use math, you show your math. This is our mathematical solution, but we have to explain that in the context of the problem. So here's the context. In 1800, according to this model, there were 337,000 people. What will the population of New York be in the year 2024? Well, this is the population based on years. What do I plug in for t here? T is the years after 1800. So 2024 is 224 years past 1800. So you plug in 224 for t, and I go to my calculator, I multiply these two, I get negative 7.84112, and I go to my calculator again, I do e raised to this power, and I get 0.000393, multiply these two, and I get 19.43. When you're evaluating here, you have to be careful that you don't round. Really, you should never round until the very last. The very last thing you do is a round. So let me show you how we can do this on our calculator very quickly. We have negative 0.0035005. I think that was the number. Yep. Times 224. So now this number was the exponent on E. So with this calculator, I can just press up, and whatever is highlighted, I press enter and it copy and pastes. For the 84 people, if you pressed second enter, you have, it'll say ANS, that'll be the last answer. So that will be the last answer that you just got, which was E raised to that number is this. I need to multiply this by that 57 number, which I forgot already, 57.993. And then I add 1 to that. So I get 27.4752. I got a little flustered here because my numbers weren't matching up to what I got, and it took me a little second to figure out where I went wrong. And this is good that this is being demonstrated right here because it's so human to make a mistake. And the mistake I made was right in the first step. I typed in this, but if you look at the model, it's negative 0.035, and I typed in negative 0.0035. So we all just have to be very careful. We don't want to lose points because we typed something wrong into the calculator. Okay, so now this is the result after I multiply those two. So here I am. I just multiplied these two numbers, and I got this negative 7.84. And that is the exponent on E, and that is being multiplied by 57.993, and that is being added to 1. This is my denominator. My denominator is 1.0228. I divide, and I get 19.43. You cannot stop here. The question was in words. You have to answer in words. What does this mean? This means that in the year 2024, it's predicted that New York will have about 19.43 million people. In New York, in the year 2020, this year, the population is about 19.45 million. How close was this to the model of this data point? So in 2020, what does the model say the population of New York will be in 2020? Well, in 2020, that is 220 years after 1800. So you plug in 220, you very, very carefully multiply. Do not round. You really have to write out a lot of decimals here because rounding will really warp your answer. 19.37. So the question is, how close was it? And pretty close. 19.37. The difference between 19.45 and 19.37 is 0.08 of a million. So only off by 80,000 people. What is significant about the number 19.875? What is significant about this top number right here? Think about end behavior. When t gets really, really large, like approaching infinity, remember t is time in years. So when t is like, let's say 500 years into the future from 1800, this e value will essentially go to 0 because you're taking e raised to a negative, which approaches 0. So 57.993 times 0 will be 0, and you'll just be left with 19 divided by 1. So what does this number mean? This means when t gets really large, p will approach this number. That is the horizontal asymptote, one of the two horizontal asymptotes of logistic functions. And according to this model, New York will never get that many people. It'll get closer and closer and closer to 19.875 million, but never approach it. Back here. Oh, excuse me. Sorry. They would have to produce another model to predict, because New York will probably exceed this, and they'll just have to look at the census data again and come up with a better model for the population that's going on right now. So maybe this model is good only for a couple hundred years. So maybe until the year 2000, and they have to develop a new model. All right. So we're right away, you're finding T. When was the population of New York 10 million? P tells you the population in millions. So we're going to let P equal 10. And now we have to solve for T. Well, first thing, get rid of the fraction. So I'm going to multiply both sides by that denominator. And these two just cancel out. On the right-hand side, you have 19.875. On the left-hand side, we're distributing because we got two terms that are being added, and you're multiplying them by 10. So it's 10 times 1 and 10 times this second term. Don't do 10 times 57 and then 10 times E. There's no addition sign between 57 and E. So you don't distribute over multiplication. You distribute to the 1, and then you jump over addition and distribute to this second one. So 10 times this 57 makes it 579. And then you're just showing your work as you solve. So you subtract 10 from both sides. And what's the next step? Divide by 579. And now what? We have to find T. Well, I can't add, subtract, multiply, or divide anything. Nothing's going to help me. T is the unknown, and it's in the exponential spot. So I use logarithms because logs are exponents. So this exponent, negative 0.035005t, will equal a logarithm. What logarithm? Log base e. In other words, natural log of 0.017029. Last step, divide by that to get t by itself. So this is our answer. T is the natural log of 0.017029 divided by this. You put that in your calculator, and you get 116. So what does that mean, 116? That's 116 years after 1800, remember. So New York's population, according to this model, was 10 million people in the year 916. And that is actually pretty close. If you go to New York's wiki page, every 10 years we have a census. So in 1800, remember, the model said there were 337 people. It wasn't quite right there. But in 1916, well, that's between 1910 and 1920, it's really close. It's very plausible that in 1916 there were 10 million people in New York. Last one, carbon dating. So this model will tell us the amount of carbon 14 left over from the original amount based on time in years. So 3 questions and then we're done. How much carbon-14 is left on an artifact that originally had 22 grams after 8,000 years? A sub 0 is the initial amount. So I replace A sub 0 with 22, and I replace T with 8,000. And this is just a matter of punching this into your calculator, and I discover that 8.357. What does that mean? How much carbon-14 is left over 8.357 grams of carbon-14 is still around today. The rest have decayed away. How old is an artifact that only has 61% of its original carbon-14 today? Well, this one may be a stumbling block for some because we have very few numbers. We know that 61% of the original exists. Well, I guess you could imagine maybe it started with 500 and 61% of 500 is 305. Or even simpler, let's start with 100 grams and 61% of that, of course, is 61. Or maybe you start off with 88.9 and 61% of that is 54.229. All three of these relationships are 61% left over. But they all just dwindle down to this. If you have 100% of something, that's 1, and you're left with 61% of something, that's 0.61, then you've got this setup. And in fact, no matter if you start with any of these three, the very first thing you would do would be to divide by 500. If you take 305 divided by 500, you get right here. So how do I solve for t? Well, the exponential part is by itself, so I convert to logarithms. The natural log of 0.61 equals this. Divide both sides by that, and you've discovered what t is. But we had to evaluate that. So I go to my calculator, I find the natural log. The natural log of 0.61 divided by negative 0.030121. 4,085. What does that mean? That means the artifact that you found in your backyard is 4,000 years old, so you could sell it for a lot of money. All right, last one. We were spelunking in France and we found a cave painting, and we determined that 17 of its original 19 grams of carbon-14 was left over. How old is this painting? Is this exciting or not really? Did someone just graffiti this a few years ago, or is this really old? Because it has a large majority left over, 17 out of the original 19. Set it up. The initial amount goes here. What's left over becomes here. Divide by 19 to solve, and now convert. The natural log of 17 over 19 equals this. Divide, and you are done. The natural log divided by this is t. But of course, we should simplify because we want to communicate to people. This isn't going to help anybody. Put this in your calculator, and that will equal about 919. So that painting is pretty darn old, 919 years old.